In the year 1054, a new star appeared in the sky. Chinese astronomers took notice and called it a guest star. For nearly a month it was bright enough to see in daylight. Then it faded and left something behind. That guest was not a new star at all. It was an old one ending. What sits there now is a cloud 6 light years across. It is the wreckage of an explosion we call a supernova. Everyone knows a supernova is a star blowing up. That is true, and it explains almost nothing. Stars are not bombs, and most of them never explode. So what actually makes a supernova a supernova? To break a star, you first have to know what holds one together. A star is not a ball of fire. It is an argument, and it has two sides. Gravity is the first side. Gravity pulls every part of a star toward its center, always. Left alone, it would crush the whole thing inward. Something has to push back, and something does. Deep in the core, nuclear fusion is running. Fusion releases energy, and that energy creates pressure inside the star. That pressure balances gravity's tendency to pull matter together. In goes gravity, out goes pressure, and the star holds still. Our sun has held that balance for billions of years, so a star is not really burning. It is winning an argument, slowly, for a very long time. Every star you can see tonight is winning it right now. A supernova is what happens the moment a star loses. To keep pushing back, the core needs fuel that pays. It begins with hydrogen fusing into helium. When the hydrogen runs low, the core shrinks and heats up. And then helium begins to fuse. Helium fuses into carbon, and carbon into neon, oxygen, and silicon. Each step is one rung on a ladder. Each rung burns faster than the one below it. In the largest stars, the final rungs take only days. Then silicon fuses into iron, and the ladder stops. Iron is the rung with nothing above it. Fusing iron gives back no net yield of energy. The core fills with ash that will not burn. This is the quiet center of the whole story. The star has not run out of matter. It has run out of fuel that pays. Pressure stops, and gravity has been waiting the entire time. What happens next begins in less than a second. With nothing pushing out, the core collapses under its own weight. A star at least 5 times our sun's mass has reached its last hurrah. The fall is fast, and it does not stop gently. The core collapses, then rebounds back toward its original size. That rebound drives a shock wave up through the outer layers. The collapse is so fast that the shock waves are enormous. They blow the outer part of the star apart. For a few weeks, that dying star outshines almost anything. A supernova can be billions of times as bright as the sun. That is why a single star can be seen from another galaxy. It is the biggest explosion humans have ever seen. This is the road most people mean by the word supernova. Astronomers call it core collapse, and the name is honest. Nothing was set alight, and nothing was detonated. Something stopped holding, and gravity did the rest. There is a second road to a supernova, and it is stranger. It needs 2 stars orbiting one another. At least one of them must be a white dwarf. A white dwarf is what is left when a star sheds its atmosphere. A white dwarf is usually about the size of Earth. It is also hundreds of thousands of times more massive than Earth. There is no fusion running inside it and nothing left to burn. It is a dead ember, and it should stay that way. But this ember has a neighbour, and it steals from it. The dwarf siphons material off its companion, a little at a time. Its mass climbs toward a point where it becomes unstable, and then it reaches that point. What follows is a runaway reaction that detonates the thief. The whole star ignites at once, rather than collapsing inward. The white dwarf does not survive it. 2 completely different roads, and both end at the same word. So which of those 2 is the real supernova? Both are, and that is the answer to the whole question. A supernova is not defined by what starts it. It is defined by how it ends. Compare it to a nova, which sounds like a smaller version of the same thing. When a nova occurs, a large outburst takes place, but the stars in that system are not destroyed. The star flares, settles down, and can do it again. A supernova is different because the star does not come back. Novae can be hundreds of thousands of times as bright as the sun. A supernova can be billions of times as bright. The size of that gap and the finality are the super in supernova. An explosion that violent does not leave nothing behind. When a massive star's core collapses, the core itself can survive. What remains is a super-dense object called a neutron star. It is the densest thing we know of. A neutron star packs more mass than the Sun into a tiny sphere. That sphere is about as wide as Manhattan Island is long. 1 teaspoon of it would weigh as much as Mount Everest. A star's core, folded down to the size of a city. That is the outcome for stars of about 8 to 20 solar masses. Heavier stars leave something else behind entirely. Their cores do not stop at a neutron star. They keep collapsing and become black holes. Meanwhile, the rest of the star keeps moving outward for thousands of years. That is the cloud still sitting where the guest star was. 6 light-years wide, and it has not finished spreading. The explosion is long over. The wreckage is still traveling. Astronomers sort these explosions by their light, not by their cores. Some supernova spectra show hydrogen lines, and others show none at all. That difference is where the type names originally came from. A supernova is classified by what its light says, and one of those types turns out to be extraordinarily useful. The white dwarf explosions all peak at a similar, known intrinsic brightness. That makes them standard candles, objects that emit a specific amount of light. Every one of them is, in effect, the same bulb. If you know the true brightness and measure the apparent brightness, you get distance. One exploding star becomes a ruler laid across the universe. Astronomers use them to see how fast distant galaxies are receding. Comparing that at different distances traces cosmic expansion over time. One last thing a supernova does is the closest to home. A star spends its life building heavier elements out of lighter ones. Then it dies and distributes those heavy elements throughout the galaxy. Supernovas are the primary means of seeding a galaxy with them. Carbon, nitrogen, oxygen, silicon, iron, the elements planets and life need. All of the oxygen in the solar system came from exploding massive stars. About half the calcium came from them, and about 40% of the iron. That is the calcium in your bones and the iron in your blood. So a supernova is a star losing an argument it held for billions of years. It is the moment pressure stops and gravity finishes the job. It is the brightest thing anyone has ever watched happen. And some of it is walking around inside you right now.